Our second speaker this morning is Mirjam Weilenmann, who's from IQOQI in Vienna, which stands for Institute for Quantum Optometry, is that right? Quantum Optics and Quantum Information. And she's going to tell us about self-tests of physical theories and foundations of quantum theory. Thanks, Mirjam.
Well, thanks a lot. Thanks a lot for inviting me and to give this talk. I'm very excited to be here, and it's been already very interesting. And so I'll tell you about self-testing physical theories, which is essentially a way to apply those networks of classical or quantum systems, or also with more general systems, but kind of an application of all those techniques that Ellie has already introduced us to. And the work I will be presenting is based on two projects. So one is with Roger Kolbeck, and the other is with quite a group of collaborators. So Marco is here, and also Miguel from here. Okay, so now why do I think that networks can tell us something about the foundations of quantum theory? And I think what comes to mind as a physicist is Bell's theorem. Right, because really Ellie already has told us that we are essentially in this graph in Bell's theorem. So as a physicist, I think of two parties, Alice and Bob, who sit somewhere space-like separated, and they are shared some system, and then they can put choose measurements to perform on this system. Okay, and then in this case, this will be a quantum system here that is shared. And then I can compare this, what would happen if I had the hidden variable model where this lambda would be classical. And as compared to Ellie, I now, when I have kind of observed variables, I also put the circles, but when in the other case, I just don't put a circle around, and this means it can be either classical or quantum, depending on what I'm considering. Okay, and so then in this particular scenario, we know that, okay, if we observe things, we can get, if you look at the outcome distributions of these measurements conditioned on the inputs, the measurement choices, we know that in the classical case, we have this usual way to find the probability. So A depends on lambda and X, and B on Y and lambda. And in the quantum case, then we have here a quantum state. So this if you're not familiar with this, it doesn't matter. It's just a way to have, if the parties are space-like separated, independent measurements that they do on some shared system. Okay, and what we know is that actually in this case with quantum systems, we can recover any such, if we think of this as this probability distribution space, we can recover everything that we can get in classically, but there is more. Okay, and then the way we usually think about this is in terms of some figure of merit. So we define some figure of merit to evaluate then the theories, and usually we do this with some linear functional in this space, where then the different theories get different values. And an intuitive way to think about this linear functional can be in terms of a game, where depending then on the essentially the outcome distributions the parties generate, they get a different score. So the way to think then is let's say now we think that the inputs and outcomes are just binary. So we can think of a referee who asks Alice and Bob questions, which will be in this case the X and Y. And depending on these questions, they will have to generate answers that they return to the referee, and the referee then has a condition to evaluate them. Okay, and the most famous way to do this is with what is called the CHSH game, where then the condition according to which they're evaluated is that when both get input 1, they should be perfectly anti-correlated, give perfectly anti-correlated answers, and in all other cases they should give perfectly correlated answers. Okay, and now it turns out that in this case, if you look at with what probability they can win this game, this is one of those ways to distinguish the theories. So here, this is the probability that the referee chooses uniformly from the set of questions. They generate their answers, and then it's evaluated according to this. And the score in the classical case is the best they can do is 3/4, whereas in the quantum case they can go up to about 85% roughly. Okay, and in the classical case, to think about the strategy, so one way to achieve this would be that they just take this random variable lambda, this hidden variable, and they just, if this is a uniform random variable that gives you 0 or 1 with equal probability, they could just output this. If they get the same variable, then in 3/4 of the cases, they're perfectly correlated, which means they achieve those 3/4. Okay, and this is a way to think intuitively about those Bell tests essentially. And then, okay, this is something that we know has also been experimentally done. So there have been various loophole-free Bell tests, three main ones that I'm aware of, where people have really kind of implemented those networks. And the difficult part, or one of the difficult part, is kind of get the networks right by really having the people far apart and space-like separation, and to kind of really get this right. Okay, and of course the network is crucial, because if the parties were too close together, they could communicate. And if they can communicate about what questions they got, of course, we would be more in this network, where of course the nature of the lambda doesn't play a role for the conditional distributions. Okay, and so this is already a place where the network is crucial essentially for us to tell us more about quantum theory, in the sense that we can rule out local hidden variable models for it. Okay, and this is kind of a way to think, okay, so maybe really these networks are fundamental in this respect. Now we can go a step further and then think about, well, so the network is important for ruling out classical theory, for instance, but could it be that the network already essentially tells us somehow that we're in the quantum world? Okay, and this turns out not to be the case, and this was realized by Popescu and Rohrlich, who found, so these are essentially the equality constraints that Eli had in his talk, just written a bit differently. And so what they found is that indeed these are not sufficient to reduce us to quantum correlations in this set. But they found what is now known as the Popescu-Rohrlich box, that indeed is way out the quantum set and wins the CHSH game with probability 1. So if you can go beyond quantum theory, but still be compatible essentially with special relativity, because you still have the right independencies, you can go further. Okay, and then this caused kind of a whole essentially research direction to emerge, I would say, where people were then looking for ways to argue why we're actually observing quantum theory and at one of those other theories, which could also make sense. And there have been many principles people have then proposed to actually recover the quantum predictions. And usually the idea is that, okay, if you would have these more general correlations, for instance, this PR box, this would have consequences, for instance, for information processing and for other things you could do. And then if you find that these consequences are unnatural, then you can essentially argue that because of this, maybe we are dealing with quantum theory and from a more physical point of view than just, okay, we don't get the thing we want. Okay, but then, okay, this I just said, but then somehow this doesn't completely work. So one thing is that there could still be non-signaling correlations that are not quantum in the world somehow, and we just haven't figured out how to build a device that generates them. I mean, just because it's unnatural, it doesn't mean that they couldn't be there, and we could be surprised. And so this is one drawback of this approach, I would say, that this we could not exclude. And the second one is that somehow the principles don't fully work, and this is something that goes back also to Miguel and his collaborators, that indeed most of those principles have been shown to recover not quantum correlations, but a slightly larger set, which is known as the almost quantum correlations. Okay, and so this way of approaching this problem doesn't fully work, and so somehow then we need something else to look at this. Okay, And so now one thing that actually we can then do is we can ask, well, maybe the Bell scenario is just not the right way to look at the problem, but maybe networks can help us. Okay, maybe we can put quantum systems into larger networks, and maybe then we can say more. Okay, and this is essentially, I would say, the idea behind a self-test of quantum theory. Okay, when we change the network, what can happen to these sets of correlations is that somehow their relation changes. So why in the Bell network there are various theories, generalized probabilistic theories that Ellie already mentioned, that get those more general correlations, for instance, having PR boxes. And these have those problems that I just mentioned. If we change the network, it may be that quantum theory is optimal among all those generalized probabilistic theory with respect to some information processing task. And then this is a new way to look at the problem. Because if we find a task, a network, and then a task on it where quantum is uniquely optimal, first of all, we can actually experimentally exclude those other theories that we could never do in this scenario. And the second thing is we can do is if we have this also points to a physical principle underlying quantum theory in kind of a new way, because it doesn't tell us in what sense other theories are unnatural, but it tells us in what sense quantum theory is special. Yes.
Can you just explain what you mean by optimal in this context?
Okay, so I would have a network, and then I would have parties who also have inputs and make outputs. And I would define, again, a game or some relation on this, some figure of merit. And then there is a maximum that you can achieve in, let's say, this generalized probabilistic theory framework. And optimal, I would mean that quantum achieves the maximal value, which in the CHSH game and the usual Bell scenarios is not the case.
Okay, thanks.
I think there's someone else raising their hand.
I mean, maybe just because there's always, can you just explain to me the thought behind that? That is, if someone says, here's an explanation for why the physical universe does something, and you say, oh, but that's the optimal way to win a quantum game that involves such and such, you know, payoffs and blah, blah, blah. I mean, what's the thought? That God wanted us to be able to play games efficiently? I mean, I just don't even understand how that connects with physics.
Okay, yes, okay. So I guess this is a step towards it, but so, okay. So of course, then there is a step going from, so the first, what I would like to do, and this is what I would say is a self-test of a physical theory, if you have a point where it's uniquely extremal in this work. And then the implications, I guess the experimental test comes relatively directly, but this point to then extract the physical principle out of it is not immediate. So I wouldn't say the game is the physical principle, but you will find aspects that you need of quantum theory and that other theories don't have, that otherwise you would find natural as well. And then I think these aspects will, I would hope, will guide me to actually find a way to physically explain it. Yes. So I guess it's a way to see where to look somehow. Yes. Okay. And so this is kind of the task we have been addressing, and we're also still addressing, and other people are as well, with this approach. Okay, so now how could we go about this? So I said, let's change the network. So let's start from this. I now named Bob Charlie for reasons that will become very clear later. But let's assume Alice and Charlie now play the CHSH game, okay? And we're in this scenario. So now how could I adapt the network to maybe see something interesting? So of course, okay, the easiest way to adapt it is to split the two. But that gets even worse. Now this is no good, because now they have independent sources, and now, for instance, the strategy that I told you before, where they use the lambda to generate their outputs, that doesn't work anymore. But what we can now do is we can actually use those sources and share whatever is shared here, in the classical case, a copy of it, or in the quantum case, a shared state with a third party. And that's Bob. Okay, we call him Bob. Now Bob has access to these. Now, if you think in this classical strategy that I mentioned before, so now, of course, still Alice and Charlie are actually not, they don't share a resource, so they cannot use the strategy from before. But what can happen is that now Bob knows what resource they get. And so conditioned on him observing that they are get perfectly correlated resources, they can now win again the CHSH game. And he knows even more. He also knows if the resources are anti-correlated. And so what he can do, what we can now do is define a game where Bob can choose whether they play a game where Alice should be and Charlie should be perfectly correlated in 3/4 of the cases, or one where they should be perfectly anti-correlated. And now if you do that, they will again win with 3/4 probability overall. Okay. And so this is a way, and in the network, it just means we add this collider here. Okay, and so this now means that we can essentially define in this larger network a game or a task where they will retain their winning probability. And now, okay, we can use this idea also in the quantum case. In the quantum case, it's a bit more complicated. So they will, in this case, when they win the CHSH game optimally, they share maximally entangled states. But there is a way for Bob to measure maximally entangled states so that conditioned on his outcome, Alice and Charlie will share a maximally entangled state. And so then there is a similar reasoning to the classical reasoning I just introduced you to, where you can then say, okay, if Bob is allowed to choose which of a selection of similar games they are allowed to win, they can retain the quantum probability from the CHSH game. And so this is what this expresses. So here Bob has 4 outcomes because we want to retain the quantum probability as well. And each of those is essentially a version of the CHSH condition that I've introduced you to before. Okay, and so this way we have a way to retain like the classical as well as the quantum probabilities. But now this is not necessarily the case if we look at other theories. Okay, and so this is exactly why then we hope that with this we can rule out other theories because they cannot retain their performance when we put this essentially collider in between. And maybe to try get a physical intuition. So one thing, I mean, this kind of means that when we have strong resources between certain parties, that somehow we can have parties in between that distribute them around. And maybe in some sense, these resources can be transmitted over longer distances. And this could be kind of maybe an avenue towards then finding a physical reason for this. Okay, and so what we find then is really that, okay, so this proposed game or experiment allows us to rule out the variety of these generalized probabilistic theories that people have come up with. And these are quite exotic versions of them, so they are quite far away from what quantum theory looks like. There are 2 main things we can essentially use for this. One is we can use the type of system composition that you use to build joint state spaces from single ones. And the other thing is that also the single system state spaces themselves can already have implications for those games. And so there are kind of there are various cases where we kind of encounter this diagrammatic situation that from before, where really these theories were more general or considered more general in the Bell scenario, but it turns out that in a different network, this is not the case anymore. So somehow this relation turns over. Okay, so I don't really want to define those theories, but one thing that okay, I said already is that they're quite exotic, quite far away from quantum theory, but there are also generalized probabilistic theories that are similar to quantum theory. Okay, for instance, quantum theory over real Hilbert spaces. This is very similar to quantum theory, and this will perform exactly the same in this adaptive CHSH game that I've introduced you to. Okay, so this is all constructed in a way that this also works. But now what we found that there is also good news, because the network itself allows us to find a more sophisticated game where indeed also the 2 of them show a difference. Okay, and this is the work that also Marco and Miguel who are here were involved in. And I want to now spend the rest of this talk essentially to introduce you to essentially how this works and what the game is to do this. Okay, so in this case, the picture is a bit different because we don't have that the situation kind of reverses in some areas, but really we essentially will get a better resolution of different theories that were not different in the Bell network. Okay, and I think this is the most interesting generalized probabilistic theory actually one can look at, and in that sense, yes, I will focus on that. Okay, so now for this we need quantum theory though, and I don't know how familiar everyone is. So essentially, what we can see is that quantum theory and real quantum theory kind of follow the same axioms, except that the complex Hilbert space is replaced by a real Hilbert space. So we work with mixed state. So a state is a density operator on a Hilbert space that is positive and has trace 1. We have a composition that is given by the tensor product. And there is an evolution. This will not be important for the talk though, so maybe we'll skip that. And measurements are then, so the probabilities, that this is something we've already kind of seen, but I told you not to pay attention to it, is given by the Born rule. Okay, so there is some measurement operators that we apply to the state in order to obtain a probability of the various outcomes. Okay. So now these are two theories and they look very similar. So then one of the questions one would ask first is, well, are they even different? Is there, what is the situation there? Okay, and they do have different properties. So if we look at the smallest system we can consider, so in quantum theory, we usually speak about the qubit, which is a system on a block sphere. And in real quantum theory, essentially, we can drop the sigma y component, so we're restricted just to a plane. Now, what happens if we want to describe several systems or a larger system, a 2-qubit system? Okay, so in the complex case, what we can do is characterize the system completely again with those Pauli measurements. Okay, so what we could do in order to find the state of such a 2-qubit system is really do all those measurements, and we get back, and we can completely describe the state of the 2-qubit system. Okay. But now in the case of real quantum theory, this is not the case. So in this case, the X and Z plane is not sufficient for this, and I think the simplest way to see it is with an example. So assume we have this maximally entangled state that I call phi plus, and it's going to come up again later. So if I write it in this way that I wrote this here, then we have this state, okay? And you can see that it's real here. There is nothing complex about it. But now, just by looking at sigma X and sigma Z Pauli matrices, I can see that I cannot really fully determine the state of this by just looking at local parts, because the sigma y contribution is there. Okay, and because sigma y is not something I can locally access in a real quantum theory, this means that somehow this theory has global degrees of freedom that cannot be accessed by doing local things, and this is what we say when we say it doesn't satisfy local tomography, because in quantum theory we can always do everything by just accessing systems locally. Okay, and so somehow from a physical point of view, this are two quite different aspects that theories may have, I would say. So then the other question one can ask, well, why did you even think the theories are the same? Then maybe if we know this, maybe it's natural to say that they lead to different correlations as well. And okay, the reason is that I've kind of already mentioned this a little bit. So if we look at a Bell scenario or another scenario where there are measurements performed on a single state, it turns out that there is no difference in the correlations you can generate. And this goes actually back quite far. So the first work I know that did such a construction is work in the 60s by Statistical. And then there were also more kind of quantum information and more multi-partite accounts of it later. The way this works is like this. So a real simulation of essentially this strategy on a larger Hilbert space can be made using this. Okay, so essentially, intuitively, what I would think of here is if you think in the complex quantum picture, what you essentially add is some control system for each measurement that controls whether you apply the measurement or its complex conjugate. And what is nice about this is then you can see that by taking the complex conjugate of this operator, that indeed it's going to be itself. So it's a real operator that we defined in this way. And for the state, similarly, we just add one of those control systems for each of the measurements, separate measurements we're gonna perform on it. And again, we can see that it's real, and we can plug this in here and see that we recover any possible correlations that we could have had in the complex case. Okay, we need a slightly larger Hilbert space, but we didn't put any restriction on anything like that. So this simulation is perfectly fine. Okay, and so then how could we distinguish the two? And the partial answer is, so this construction doesn't go through anymore naturally in the bilocal network, and so this is a candidate where we can again look for a difference. And this is what we did. So essentially what we were looking for is to find a distribution here at the boundary of the quantum set somewhere that seemed to be kind of genuinely complex in the way it was constructed, and then essentially show that this cannot be recovered with real quantum states and measurements. And this is the candidate distribution. Okay, so again, what we have a similar intuition to before, that Bob, the party in the middle, will essentially swap maximally entangled states to Alice and Charlie. And then Alice does a measurement that is all three polys. So this seems genuinely complex, and a similar thing for Charlie. Okay, and this is now a candidate where you can think, okay, maybe this is difficult or not possible to recover in real quantum theory. Okay, I added a bit about the intuition, why this distribution. So it turns out that this distribution, there is a Bell inequality that it satisfies maximally, which is called a triple CHSH inequality. And there is a result, which is a self-test within quantum theory. So which means that if you have this distribution, you can essentially know which states and measurements you had within the quantum formalism. So now, rather than testing which theory in a more general framework, in self-testing in quantum theory, you usually test which state and measurements you had if you generated a certain distribution. Okay, and it turns out that with these states and measurements that I mentioned before, they essentially do such a self-test for in the Bell scenario. Okay, and then essentially what our candidate distribution is essentially taking these apart and putting Bob in between to swap the entanglement around. Okay, so I think this is as much intuition as I can give about it. Then it's really about kind of doing the computation and seeing that it works. Okay, and this is what we did. So what we tried then is to see if we have here real states and real measurements, can we recover this distribution P bar? And as was kind of clear from what I said before, you cannot. Okay, we have here a slightly more general scenario, because in addition to having independent sources, we also allow shared randomness. So this is okay because somehow we can still prove the result, and so it's more general. But also for experiments, this is very important, and we would like to have this experimentally tested, because somehow if you have independent sources, you still have to synchronize your experiment so that in the end, I mean, one doesn't, not one source prepares a photon today and one prepares one tomorrow, but that they coincide at the right time at essentially Bob's station, so he can do the experiment. And so a synchronization is kind of always important, and so this was also important that we actually do this slightly more generally. Okay, and so what we then assume is, instead of having a product state, we have essentially here a separable state. So this probability one could think about in the state. The important thing is there is no shared quantum resource between all three. Otherwise, this wouldn't go through. Okay. Also, one thing I want to mention, so we don't have a dimension bound here on the real quantum thing. So it's really saying that with real quantum systems, a measurement of any dimension, you cannot recover this. So it's really a gap and something you cannot do. Okay, and the result is also, so this is just for this specific distribution. This is also noise robust in the sense that we can even find a large enough gap so that this can be done experimentally. Okay, and this relies on convex optimization techniques to find good bounds on the real quantum systems here. Okay. Yes, I think then, yes, okay, there have been experimental implementations as well already. So I'm aware of 3 actually. The first one was very short after our result came out. This is with superconducting qubits, and in this case, yes, everything is on one chip essentially. So in this case, it's not so clear that this independent sources assumption has been implemented yet. And then there are 2 more. So these are from different papers from these 2, and they're with optical experiments. So in this case, the sources are really independent, and this part works. There are some detection loopholes open though. So somehow with different loopholes open, things have been done, but not in a loophole free way as we have with the Bell-test. Okay, and so somehow, yes, this has been partially refuted, that we cannot have a quantum theory over real Hilbert spaces. Okay, so summary. So okay, so I hope to have convinced you that networks are a very useful tool if we want to see about ruling out different of those generalized probabilistic theories people are researching. Okay, and these also include theories that, for instance, in the usual Bell scenario, are more non-local than quantum theory. At the same time, and specifically quantum theory over real Hilbert spaces can be excluded in this way, and this has even been experimentally done with loopholes still, but I think there's good indication that this will be closed soon as well. So this works. Okay, now what more is there to do? So I think a lot actually. So for one thing, there are other theories one could come up with in this generalized probabilistic theory framework and theories people come up with. And so really having a statement that quantum theory is, if possible, uniquely optimal somewhere would be very powerful, because it could rule out also future theories we can come up with. And so this is I think still a very interesting question, whether there is such a network and such a task where also many things still have to be clarified. Then in the next step, it would be nice to then bring these insights to some axiomatic way to recover quantum theory from features that we learn from these network tests. And as a last thing, I think this also shows that somehow these networks all of a sudden can bring us new avenues to look at quantum foundations. And I think we've just taken essentially the next general network after the Bell scenario. And I think looking at really a variety of networks and looking what else they can tell us, I think is very exciting. And I think a lot of research potential is still in this approach. Also now that we have all those techniques that Ellie has introduced us to. And so I think this is very exciting, and I'd like to thank you.
Thank you very much. Are there any questions from the audience? Yes.
Very quickly, because this is not the way I think about things. I would have thought, at least theoretically, not experimentally, instead of CHSH, GHZ would be better. I mean, it's cleaner, right? The restrictions for GHZ are cleaner. Is that something people are looking at? Greenberger, Horn's Island, 3-part.
Triangle.
No, the triple entangled state with perfect correlations. The Greenberger, Horn's Island. People don't know that. Oh my gosh. Okay.
The quantum people presumably do know.
Isn't that a natural thought to how the things go with that? It's just it's a stronger constraint. It's a non-statistical constraint, but if she doesn't know what it is, I can't ask.
No, I do know what the GH set state is.
So she does know. I don't know because I'm not a quantum person. I'm a statistician.
You don't know Greenberger, Horn, and Zeilinger in this conference? I'm sorry, this is a little.
No, this room is like quantum people and the speaker answer.
Okay, maybe I can write this down. No, there is a thing called the Greenberger, Horn, and Zeilinger state, and it's a state that instead of having just this maximally entangled state that I mentioned, so what we were looking at in the Bell scenario is a state that looks like this. So we just have two systems that can be accessed. So this was the phi plus I was working with. And then there is also a GHZ state. I guess we normalize as well.
No, that's not it.
That is not the GHZ state.
It's a superposition of 4. It's an equal superposition of 4 different entangled 3-particle states. It's not a two.
So you mean the W state? Maybe this would be.
I mean the G.
0, 0, 1
Someone ought to give a
plus
talk about this.
1, 0, 0. And then I guess you have the one. Do you mean this one or no? As a state.
Yeah, that one.
Okay, so I think this is okay. So maybe I have a different terminology. So for me, this is a W state, I think, or in the W state family, maybe. So
I mean, you need the right plus
yes.
and minus signs. You need the.
Okay. You have some. Okay.
Not just any state like that.
C D with okay. With some coefficients. So. Okay.
But you get perfect predictions for. You get perfect predictions, not statistical predictions for.
Do you mean the Mermin square, maybe?
Mermin wrote a nice paper about GHZ. So if you've read Mermin, you should know GHZ.
Okay, so I think, sorry?
No, the one, this one is 3.
The Mermin test, Mermin's inequality.
3. Alice, Bob, and Charlotte, you have a 3-particle state entangled.
Experimentally, you never get perfect correlation, so it doesn't make any sense. So you cannot violate, you cannot prove that Presque mechanic doesn't hold using one of these inequalities, but if you go to the experiment, you will find perfect correlation.
That's why
it is an inequality.
But that was my original point, to saying at least theoretically, I understand there are experimental problems. It's harder to make GHZ states, okay? But theoretically, you have these perfect predictions. They come out of quantum.
Theoretically, you don't want to produce a perfect GHZ state, right? I mean,
it's just like the perfect correlation.
Yeah, but it is not robust. It is not robust with respect to noise.
So what?
But
I'm
you
just
cannot
talking
do
about
it.
it. You have a theory, and you can ask if there are other theories that make the same predictions. Forget about it.
Okay, so I think maybe.
Real quantum theory also makes the same prediction for that experiment. I don't think.
Okay, I think, okay, maybe.
Sorry, I thought it was a simple question, but it wasn't.
No, it's okay. I mean, I think I thought you were speaking about the GHZ state, and apparently not. So I think we had have some different terminology. Maybe we should talk in the break. maybe what I can say quickly. So in principle, so the trick of whenever you have a bipartite thing, the trick with putting Bob in the middle and seeing whether you get good separations. We have also tried this for other Bell inequalities. So this works. Now, if you're asking about going to a three-partite test, then I think the analysis becomes more complicated. And so this we haven't actually done, and I don't know. But in principle, I mean, the playground is huge now. You can think if you have a three-partite thing and you share a state, you can then ask, well, how if I put more parties in between, can I maybe do a similar argument? But I think it's not as natural in this sense, because we know this Bell state measurement and we know that we have entanglement swapping, and this is something that the idea was very much based on. And for instance, if you have three parties, then it's not so clear where you would put the person in between that mediates and how you combine the different sources. And so I think it's very interesting, and there are many things to be answered there, but at this stage we have not looked into this.
Okay, well, I guess we're out of time now, so let's thank our speaker again.